right, we have this new concept called moment of inertia, which is actually a simple concept, not too complicated. So for angular motion, angular suggests rotation. Okay, angular motion refers to motion. So rotation, right, means if you have a body, a rigid body, you are rotating, means you are turning rotation. Okay, so if you have rotation, you have angular motion. Remember, so far we've been covering linear motion. That means you are moving along straight lines, okay, or projectile motion. Now, now we are rotating about some fixed axis. So for angular motion, we have angular displacement. The right as theta is the angle through which a point revolves around a center. So if you rotate, right, this theta here is our angular displacement. We also have angular velocity. So the term velocity suggests how fast is this rotation going on. Okay, how fast is it? Then we also have angular acceleration. So from the term acceleration, it suggests how fast, how much this angular velocity is changing. Okay, so it's the same displacement velocity and acceleration concept that we covered. Just that now we are going to apply it for rotation. Okay, and you will see a lot of similarities, which is why it shouldn't be too understand for this. Okay, so for average angular velocity, just like the previous definition that we had looked at before, average is you take the difference between the displacement divide by the time taken. So difference between displacement and difference between time. Okay, that you will get the average. For instantaneous, same thing. When we see things like instantaneous, right, you will be differentiating something. Okay, so there will be some differentiation involved. So same as our linear kinematics, instantaneous angular velocity, we will go and differentiate the distance. But now because we are talking about angular, right? By the top here is the, and then moving on for acceleration, definition for average, same. Take the difference between angular velocities divided by the total time taken. Okay, that's how you get this delta omega over delta t. And for instantaneous angular acceleration, same thing, instantaneous, you will differentiate. And down here, we will differentiate velocity, angular velocity. So we come to rigid body rotation. Rotation of an extended object. Extended object means object that has many points. So far, most part of the course we have been studying points, correct? Even a car, we assume it as a point. But real life, right, objects, they have many points on it. So for example, this shape here, you can see it's not a point, right? Like there, you can imagine many points on this. Okay, so this whole thing, right, is a body, is a rigid body or an extended object. Different parts of an object have different linear velocities and acceleration. So when this thing rotate, right, it can be rotating at the same rate, the whole object, which means it will have same angular velocity. But if you talk about linear velocity or acceleration, right, you compare different points on it because they are different parts of the rotation, they will be different. You have a different value. Okay, for example, this outer point, right, we have to rotate this object, it will be moving much faster than some point that is near center of rotation. Okay, you see the center of rotation, maybe it's going at this speed, okay, slowly. But the one outside, right, to follow with the rotation, right, it will be going super fast. Okay, so you can imagine a running track also. Okay, if you are running at the most inner lane, of course you run slower, right, to keep up with the one outside who has to run much faster to be um, to take the turn. Okay, same turn as you. Okay, so they have different linear velocities. So for this study, we assume that object is rigid. Rigid, that means it won't change shape. Okay, non-deformable, internal motion neglect. Pure rotation motion. For this topic, we are talking about pure rotation motion. That means it's rotation about fixed axis. Pure rotation means this axis, right? for this study, it will always be here. Okay, so we are always rotating around this point. Okay? For rotations, they are not pure rotation. It can be a combination of translation and rotation. For example, rolling motion, which we will be going through next time. Things can be translating in space, can be moving, right? And also it is rotating. So pure rotation means rotation only. Every point has the same angular speed and angular acceleration. So if you talk about angular quantities, right, every point will have the same value. It's the linear quantities that will have different value. So for rotation, it's more convenient to use polar coordinate. For rotation in general, we'll be using polar coordinate. Here, easier form and easier way to write things. Okay? Or you can see as polar coordinates is actually made to study circular motion. Okay? So just a revision. The unit of theta is radian. Okay? This theta here, S equals to R theta. S is this arc length. Theta is the angle, and it must be in radians. In maths or physics, right, or engineering, when we see theta alone now, without tangent, cosine, sine in front, right, usually this theta alone, right, will be in radians unit. It's only when we have sine, cosine, tangent, you can use angle because why? The calculator will account for it. So when you select the mode, right, you choose the mode. Then the calculator can account for it. But if you don't have those sine, cosine, tangent in front, right, there is usually must be radians. Okay, so don't use the wrong value, right? If you put in degrees, it will be wrong value. Must be in radians. Okay, 1 radian is the angle subtended by arc length equal to the radius of arc. Trying to say that 360 degrees will be equals to 2 pi radians. And this is how you count. Okay, so you need to know how to count. If you get things in degrees, you need to convert to radians first before you can put into this kind of form. Okay, so this part is when a rigid body rotates about fixed axis, every particle in the body moves same angular speed. So same thing for angular quantities, every particle right moving same. Uh Michael, is the lesson being recorded? No, it's not being recorded. Yeah, thanks for answering. Because for all the lessons it's recorded. Okay, the admin has instructed not to record because of PhD. Okay, so none of the lectures are recorded. That's what they told me. Okay, to record. But if you have any issues or questions you need to ask me, right, you can always um, email me and ask me. And I have already made the slides in such a way that most of them are key, okay, so it won't be so confusing. But in any case, if you don't know anything, just feel free to email me. Okay? Okay, let's continue. So from this, right, you see for rotation, the angular quantities will remain the same. For example, angular speed. Okay, all these will remain the same. But all these V equals to the linear velocity. Okay, if we are talking about this point here, this whole object, we are looking at one point on it. Okay, this point, if the object rotates, it will follow this blue line. Okay, but at this instant, right, this thing is rotating. You have this angular speed, but because it's rotating, it's also going to have this linear velocity, okay, which is equals to r omega. Because this is a circular motion, right? We have learned that v equals to r omega. Okay, and then this object can also have acceleration. For sure, it's going to have radial acceleration, or rather centripetal acceleration, because it is moving, right? Not real. And radial acceleration will be equal to r omega square or omega square r. In the same direction as the linear velocity, we may also have this tangential acceleration. if it is a non-uniform circular motion. Okay, and that will be equals to R alpha. Okay, so this is how they are all related. So these are the formulas again. To turn out S equals to R theta. S is the displacement. Theta is the angular displacement. So it's related in this manner. You see there's a pattern one. Okay, so for velocity, again, it will be radius times the angular counterpart. Okay, so angular velocity E equals to R omega. For tangential acceleration, same pattern. We'll just multiply by radius. Then is the angular counterpart here, the acceleration. Okay, then for radial acceleration, this one is what we have. Equals to v squared over r or r omega. Okay, this is what we had learned last time when we talked about circular, essentially a circular. The formula stays. Then on the right here, um, if we would need to talk about it in vectors form, right? When we want to know the direction and things like that, actually it is omega cross r. Okay, remember our cross product? It will be used like this. Okay, if we are going to use it in vector form, it will be omega cross r. This one will be alpha cross r. But if we are going to get the magnitude only, let's say you want to find a linear velocity, it doesn't matter. You can take radius times omega, omega. You are still going to get this. Okay, but if you do a cross product, it will be different. So for rotations, right now we come to kinematics. Remember our kinematics is the study of motion, right? That time we are talking about linear motion. For rotational motion, right, we also have kinematics. We can study how fast it's going at a certain time, 5 seconds later, how fast it will be rotating, right? And then what is the angular acceleration at the time is so we can also study the motion of kinematics. This is called rotational kinematics. Okay, and in the same manner, we will be deriving some equations to study this rotational kinematics. Remember for the linear one, we have four equations, right? Four equations to for rotation. I'm not going to go through so much on the derivation. Okay, just very briefly, then we'll jump straight into it, which is more applicable for us. Like. So it is derived in this manner. Angular acceleration, basically you differentiate your angular velocity. Okay, then you can shift things around. You look like this. You d something on the left, and then d something on the right. This manner, right, you can integrate this. Okay, and then you set some boundary conditions. You let omega equals not at the starting time. What will you get? You will get something like this. Okay, so omega equals to omega naught plus alpha t. Don't you all find this quite familiar? Okay, this is analogous to our v equals to u plus at, right? But now, whatever quantities, right, we just change to angular quantity. Okay, then you will see the other side. Okay, we continue deriving. Omega equals to d over dt. Basically, you differentiate the angular displacement. Same thing, you push to the other side. Both sides got t, right? You're going to integrate and then look at what we have here. We have theta equals to theta naught plus omega naught t plus half alpha t squared. Also very familiar, right? Essentially, it is almost analogous to our linear counterpart, linear equation. Just that all the quantities, right, you switch to the angular quantity. Okay, so it's very similar to S equals to ut plus half at. Okay, very similar to that. And eliminating t, same thing, you'll get something like this. Omega t equals to omega naught. Omega square equals to omega naught square plus 2 alpha. This is basically our displacement, angular displacement. So this is very similar to v square equals to u square plus 2as. Okay, so you see all the equations, they are very similar. Whatever we have studied in the first lesson, right? You just need to know that, know how to use those, then you can do this rotational kinematics, no problem. Just that now everything, we are instead of talking about moving straight lines, right? We are talking about rotation. That's all. Okay, so there's one-to-one correspondence between theta and x, omega and v, alpha and a. Okay, so angular parts on the left, these are all linear quantities, angular quantities. So you see, they all look very similar. There's a fourth one, it's not written here. The fourth one is also correct, it's also true. Okay, it's not written here. You can go and write it out on your own. Basically, there are four equations analogous to these four equations. Thus that everything that you can change, angular quantity, right, change. Only one thing don't need to change lah, time, because time there's no such thing as linear or angular, right? Time is just time. Then the rest it will be changing from linear quantities to angular quantities, and it will be correct already. Okay. Okay, then vectors, omega and alpha. Omega and alpha are vectors. Okay, so this is angular velocity, angular acceleration. These are vectors, which means, right, they have directions. Okay, they have directions. But when something is rotating, how do you determine the direction? Cannot be the direction keep changing, right? It's always rotating. So this direction, right, is determined by our right hand rule. Our right hand rule. So how does it work? Look at this. If something is rotating this manner, if you see from the top, it will be rotating counterclockwise, right? You just use your right hand, your fingers, the curved part, right? You follow the rotation. Okay, then wherever your thumb is pointing, right, that is the direction of this vector. Okay, so for rotation that is rotating like this, omega, the angular velocity, if you want to refer to the direction, right, is pointing upwards. Okay, so following the same concept, if this gear here is rotating the other direction, use your right hand rule, thumb in the end will point downwards, right? So direction of this will be downwards. Okay, so far I can follow. If for any questions need me to explain again, just type in the chat. I can explain again. Then for acceleration, right, angular acceleration. Just now we were talking about angular velocity. For angular acceleration, you see if this thing is rotating like this and is speeding up, that means it's rotating faster and faster and faster in the same direction. It means it is the acceleration is in the same direction as the velocity. Okay, that's why if the velocity is pointing up, angular acceleration will also be pointing. But the slowing down this part is the slightly more confusing part than the rest. Okay, if it's rotating like this, the velocity, if you follow your right hand rule, right, is going to point up. But where is the acceleration point? This thing is rotating like this, but slowing down. That means the acceleration is in opposite direction, right? When something is slowing down, you will have negative acceleration. That's why this angular acceleration will be pointing downwards. Okay, so it will be pointing downwards. Okay, any questions? Actually, this is a shortest shortest topic. Let's split this up into many topics. Okay, so 11, right, is basically on rotational kinematics. But because we have already studied kinematics, rotational kinematics will be easy for most of you all, okay, if you know your kinematics well. Okay, so since we end so fast this topic, right, we will go through maybe two supplementary questions. Okay, so let's go through supplementary first. An airplane propeller is rotating at 1900 RPM. Compute the propeller's angular velocity in radians per second. How many seconds does it take for the propeller to turn through 35 degrees? Okay, so you see, this is you can tell that this is a angular kinematic kind of question, right? Something is rotating, and then they want you to find out what is the speed rotating after some amount of time. Okay, so this is kinematics, but in angular form. Okay, so part A, compute the propeller's angular velocity radians per second. This one, if they never ask you to compute in radians per second, you also must change. Basically, you need to change your units to the correct form first. RPM need to convert to radians per second. Okay, so this is how you convert. 1 RPM equals to this amount of radians per second. You just need to know one round, right, is 2 pi. Okay, from there you can convert already. And minutes to second, so all of you know how to convert. Okay, so you follow that logic to be able to convert angular velocity into radians per second. Once you have it in radians per second, you can apply your kinematic. Ask you how many seconds it take from to turn to 35 degrees. 35 degrees is angular displacement, correct? How much it has. So it's given to you. This is given to you, okay? Angular displacement. And then the velocity, the angular velocity, they have already given to you also. Okay? In this so we will go and find out which is the kinematic equation for us to use. Okay? Of course, don't forget this degree. Convert to radians first. Okay, convert to radian first. In this question, there will be no acceleration. Okay, they just tell the propeller is rotating at speed, right? Never change the speed. So there's no acceleration. So the equation to use is this one. This is from our S equals to ut plus half at squared equivalent. Okay, S equals to ut plus half at squared equivalent. Okay, so from there, your A, which is the alpha, right? Rho. So in the end, you only have S equals to U. U is this one. I'm reading out in linear quantities, but we are doing in angular quantities. Okay. So from here, we will be solving. That will be the time taken. Okay, any questions? If not, then we look at another question. Okay, question 3. A bicycle wheel has an initial angular velocity of 1.5 radians. If its angular acceleration is constant and equals to 0.3 radians per second, okay, what is the angular velocity at t equals to 2? So what angle has the wheel turned between 0 and 2.5 seconds? Okay, so part A, they tell you the angular acceleration is 0.3. Initial angular velocity is given by this. And then the time, right, 2.5 seconds. So you see, you are given 3 quantities, right? Confirm can find the fourth one. Okay, same as your linear kinematics. So given 3, find the fourth one, choose the correct equation to use. It asks you what is the angular velocity. So this is the equation that you're going to use. This is the equivalent equation is equals to u plus at. Okay, t equals to u plus at, but in angular form. So initial angular velocity given, angular acceleration given, time is given. Okay, so if you go and do this, you'll be able to find the angular velocity at 2.5 seconds. Part B, what angle has the wheel turned between 0 and 2.5? So what angle, right, they are asking you to find angular displacement. How much has it, right? But this one is in the form of angle, because so this is to ask you find angular displacement. So when look at your equations, which one to use, you can use this one. Okay, this is the S equals to ut plus half at squared equivalent. Okay, but all in angular quantity. Okay, when put in your calculator, you will get your answer. So it would have rotated 4.69 radians. Okay, but for part B, you see, there's another equation that you can use. Okay, which is this one, S equals to half U plus VT. Remember, this is our fourth equation. Why this one, both equations? Because you realize you have more than three quantities, right? Actually, three is given in the question, but in part A, you have found the fourth one already. So you have more than enough to choose from. Okay, you have more than enough to choose from. That's why if you use the other equations, right? The other equation, you also realize if you have more than one choice, to find the same answer. Okay, any questions? The other questions I will same thing. I let you all go and read on your own. Okay. Then if there are no questions, we can start on 12 already. Okay. I hope today can end earlier lah. We end earlier lah for you to rest. Okay, any questions for 11? Yeah, so I will start on 12. Yeah, close this and we start 12 now, okay? Okay, let's start 12. So it's basically still about the same topic lah, or same topic. That's why it's part 2. But this one is more of moment. When we rotate things, right, we cannot run away from this thing called the moment. Okay, and what exactly is this? Take a look. Consider a rigid body as a collection of small particles rotating about fixed z-axis at its angular speed. The kinetic energy of any particle, right, will be given by this half mv squared. This one we already know, half mv squared. And from here, right, this v, change it to r omega because we are rotating, right? So this linear velocity we can change to r omega. Then it will look something like that. Okay, so the total kinetic energy is just the summation of all the particles. So it will look something like that. There will be a summation sign. But basically it's like the same thing now. Okay, just that you sum all up. So kinetic energy can be written as this. Same thing, half mr square omega square. Then if we write it in this form, right, it's half mr square omega square. If we write it in this form, half I omega square. This form, right, will be very familiar. Okay, because for the linear part is half mv square, correct? Then for rotational objects, the kinetic energy will be half I omega. So you see, V analogous to omega, but M, right, will be analogous to this new letter here. We'll call it the moment of inertia. Okay, so this I, right, related mass. Okay, this I will appear when we are rotating something, and it is defined as this. Because you see from this formula, the I, right, I actually replaces this particular expression, mr squared. Okay, so this is our moment of inertia, mr squared. So for an extended rigid object, we will sum it all together, same thing, mr squared. And then if we do integration, right, it will be r squared dx. It's still the same dimensions. Okay, we have r squared here. You also have an m here. Okay, so same dimension. Just that if we want to sum things, right, for the general form, we will always do an integration. This is just rewriting this. For mass, right, you can split into density and volume. Okay, this is just a writing of it. So this is the formula for moment of inertia. So what is this moment of inertia? More details. The measure of the resistance of an object to changes in its rotational motion. So moment of inertia is for rotation. Just as mass is a measure of the tendency of an object to resist changes in its linear motion. So moment of inertia is the quantity we use, right, for resistance when we talk about rotation. Okay, mass is sort of the resistance when we talk about accelerating something, right? Linear form. Okay, so it's related in the manner. Mass is an intrinsic property of an object. That means mass cannot change. Whatever the mass is for the object, right, you bring it anywhere, right? How you move it, the mass stays the same. But this moment of inertia, it depends on the physical arrangement of the mass. Because if you look at the formula for I again, right? Go back to the actually mr squared. Okay, so it depends on the mass, but it also depends on the distance between the point of rotation and where the point is. Okay, that's our r. So it depends on the radius also. Okay, if you are far away from the point of rotation, you are going to get higher moment. That's what is right. Okay, it depends on axis of rotation. This is the dimension. This will be the units. Let's take a look at one example. We can see for the same setup, right? How different the moment of inertia will be. You were to just change the four small spheres, each of which may be regarded as a point of mass 0.2 kg, are arranged in a square 0.4 light connected by light rods. Light rods, no mass, they want you to think of it as no mass. Find the moment of inertia of the system about an axis, so about three axes. So part A is through the center of the square perpendicular to its plane. So we have these four spheres, right? Part A is, imagine this thing is rotating about this axis. So for part A, right, you imagine a line, right? Imagine a line, your pen, right, poking through your screen. That will be the axis. So how will this thing rotate? It's gonna go like this, right? The entire structure rotate like this. Okay? Because the axis is poking into the screen. Okay, so how do we calculate that? Formula is mr squared, right? Now here, this is the formula. So the key part is going to find out what is our r square. Okay, so if this is the axis, you see for each sphere, right? What is the distance? That means the r. Okay, the distance is the r, the radius, because if you rotate in circles, right, that's gonna be the radius. Right? So we want to know this length. That's why we can apply our mr squared. Okay, so for part A, basically, this is our r. Okay, then in this solution, right, they never write as r. The r, right, they write as a. Okay, so that's what we are trying. Up to you to label now. Okay, but so this a is our r. How to find a? Basically, is our Pythagoras theorem. This one is 0. All right, half of it is 0.2. That's one side of the triangle. So it is 0.4 divided by 2 is 0.2. side square plus the side square will give you the hypotenuse square, right? Which is what we have to find. Okay. And then we never take square root. You know why? Usually Pythagoras theorem, you want to find the length, you take square root. But down here, we only need the answer in terms of the square because later on we know we are going to use the formula mr square, right? So there's no point trying to square root it. Okay? Just straight away apply. What is the moment inertia for this thing? You see how we did one for one sphere, right? There are four spheres here. All of them are rotating about this. So how to find the moment structure? You take 4 times our mr square. In this case, is a. Okay, so you see this a square here. That's why they never go and square root it because you can straight away put inside and do. The mass of each sphere is given. So if you put into this formula, you're going to get a moment inertia for this particular setup. Okay, this setup where it's rotating about this axis. Let's put to the screen. Okay, then for part B, same structure, but now we rotate about an axis bisecting two opposite sides of the square. Axis along line AB. So instead of just now that one, right? Now the axis becomes this line AB here. Okay, so if this is the axis, the structure, how will it rotate? It will be rotating in and out of the screen, right? Rotating. I cannot draw lah because this is a 2D plane. Okay, but you have to imagine this is the axis, this line. This thing will be rotating in and out, okay, of the in and out of the screen. The other side also lah. So they will all be rotating in and out of the screen. So to find the moment inertia of that, we need to ask ourselves what is the R that we are looking at. Okay, the R we are looking at for part B is actually this is the R lah. Okay, the one in blue. Okay, that's the R. Because different circles already, right? Now the circles we are talking about this one. Okay, the one in blue. Okay, that's our R. This R is easy. Like you just take 0.4 divided by 2, you are gonna get it. Right? That's what we are doing. Same thing with 4 spheres, by 4 times mr squared. So we're gonna get point inertia for this. You see, same structure, but you take differently, right? You will get a different moment of inertia. Very different. Okay. Then for part C, now the axis passes through the centers of the upper left, lower right spheres, and 2.0. So it's like that. This dotted line here, this dashed line. This dashed line. So now this thing is rotating. This is the axis. It's gonna rotate something like this. In is diagonal and then in and out of the screen. I cannot draw it because it's 3D, but you must imagine, okay? So for this particular case, right, only these two spheres, the bottom left one and the top right, they are rotating. Can you see? The two spheres that cannot cut through the line, it will not rotate at all. It will not move, right? Because the axis is through them. Okay, so it will not be rotated. That's why for moment of inertia calculation, right, it will not be counted. Okay? Because if you apply mr square, the r 0. There's no distance to the axis. Right? So now we only have two spheres to consider. What then you have to ask yourself, what is the r? What is the distance to the axis? Okay, so it's this one, distance to the axis. Again, is the same a that we were talking about in part A. Okay, but now we have two only instead of four. So the moment of inertia for this, you just take 2 because only two spheres times mr square. Okay, same values, just put in. Going to get a moment of inertia. Okay, so now we go into the next section. How to calculate moment inertia different shapes, different objects. We'll be calculating using a general formula. This is the general formula, right? One inertia equals to integral of r squared dx. This is the general formula. Then we will be coming out with different expressions for different shapes. Okay, so I will briefly go through how to use this to calculate. Okay, so for a rod like this, okay, for a rod of length L, the whole thing is length L. Again, for integration, right, we always want to chop it up into many small. Okay, so we chop it up into many small pieces. One piece, right, length, we'll call it dx. Okay, just one small length, call it dx. Then let's say this thing is rotating about this axis, randomly placed or arbitrarily placed. The distance from the left end to the axis, we call it h, and therefore the distance from the axis to the right end will be L minus h. Okay, whole thing minus this one. That's why L minus h. Okay, then somehow we need to deal with this dm, right? So we need to find an expression, change this so that we can perform the. Okay, so this is the relationship. dm equals to m over L dx. Basically, it's by proportionality. A small chunk dm, right, over the total mass equals to a small chunk length over total. Okay, actually, the m is down here on up downside. Okay, this is our proportionality. Then with this, right, you sub this dm here. Okay, you sub this whole thing, up inside, go inside. Okay, that's why you will get something something dx. Okay, which is very nice for us to perform integration. And we will integrate from minus h, is the left end, to the other end because we want to find out the more inertia for the whole thing, right? L minus h. From here, right, you have some x expression here, then dx. Confirm can solve this integration already. Okay? So you will go and solve this integration. In the end, you will get this expression here. So this I equals to something. This describes the normal inertia of this object. So it depends on what h is, what L is. Okay. Then there's a rotating rod, right? This is the expression here. If you go and take a look at some special case, let's say h equals to 0. You want to know the case where axis is at one end of the rod. So imagine this is a rod. If you rotate about this axis, right, that means the entire rod is rotating about the fixed axis. The entire rod is rotating. That will be subbing h equals to 0 into this equation because essentially there's no h. Okay, we're going to get I equals to 1/3 ml. Then for another special case is, what if the axis is through the center of the rod? Means the rod is rotating about this axis, like a helicopter propeller. Okay, so it's rotating about this center. For this case, right, we notice that the h will be L over 2. H is the length from left end to axis. That will be L over 2, right? So if you sub inside, get rid of the h, you'll get I equals to 1 over 12 mL. To compare these two, okay, same shape or different axes, they have different values, right? But also another thing you can observe, this one, when the axis is at one end, it has a higher value, much higher value than the one center, correct? Because I is expected to be highest when the axis is one end, since the mass are now furthest away from the axis, lowest when the axis is at the same. It's like some resistance lah. You try to turn something, right, and then a lot of mass is far away axis. You're going to feel very high resistance. Okay, you're going to feel very high resistance. That's why um, if you want to rotate things, right, the mass should be placed closely to the axis. Okay, can also imagine in real life, if you try to turn something like, let's say you go a cold storage and do this kind of, like, you do the trolley, then you want to buy very heavy, say few packets of. You imagine empty trolley, then your detergent, right? If you place the closest to you, want to rotate the trolley, right? It will be the easiest. Okay, least resistance. But the same amount of detergent, right? You go and place it towards the furthest end, right at the tip there. You try to rotate your trolley, you will see, you will feel the difference. Very hard to rotate. Okay, same mass, but because you are trying to rotate, imagine you are the axis, right? But all the mass is pushed further away from you. You are going to feel that it has very high resistance. Okay? And it will show in this mode of image. Okay? Yeah, so that's for rod. Then we continue the same method for other shapes. Okay? So now we are doing cylinder. A hollow cylinder has inner radius R1. So imagine there's a hole inside. Okay, there's a hole inside. On the middle, where the hole ends, right? Got R1 down here. And then from the middle to where the cylinder is, right? Furthest point there is R2. And this whole thing, we call it L. Okay, then we want to work out the more inertia of this center. So again, we apply this R squared dm. But we need to change this dm to something that is friendly, right, and doable. How to change it? Okay, we'll write out something to change the dm something more doable. Down here is mass equals to density times volume. Okay, mass equals to density. Rho is our density. Volume of this particular single strip, right, given by this. L, which is the entire length, times 2 pi r, that's the circumference of this strip. Okay, then times the thickness of this strip, which is very small, okay, but there is some value to it. That one is r. So if you this thing, right, whole thing go and replace this, you're going to get something that you can solve. And you're solving from R1 to R2. Basically, the part that has material, hollow part you do one. So you solve from R1 to R2. Okay, you can solve everything, you get this expression over, which depends on what is the radius, inner and the outer radius. Okay. Then again, from this same expression, right, we can go and look at special cases. Special cases like the extreme cases. So the first one is hoop or thin cylindrical shell. This means, right, the hollow part is super big. They almost only got one material left at the outer end of it. So the hollow part is super. So now hollow part super big, right? That means you let the R1 equals to about the same as R2. Right? Remember R1 is where the hollow part end. Now it's like huge, right? One thin. So everything is equals, you just write as R. To sub inside here, right? Normal inertia will be mr squared. Then the other special case is if the hollow, there's no hollow part. Okay, basically the R1, right, that we are talking about the hollow part, 0, right? So this is our solid cylinder. Sometimes we call it a disc. It look like a disc. So R1 equals to 0. If you sub this inside here, normal inertia will be equals to half mr squared. Okay, so these are some special case. And if you go and compare these two items, which one has a higher moment? This one, right? Why? Because they have the same mass. Assuming they have the same mass, for this hook, right, all the mass is flush to the extreme end. It's all flush to the extreme end at this point. Whereas this one is nicely distributed, okay, across. So the one with a lot of mass further away, right, always have the higher moment. In other words, higher resistance. Yeah, so that's our cylinder. We can also do the same for a sphere. So let's say we have this sphere of radius r and mass m. So how we cut this, right, is we cut it into like all these. We cut it into small discs. Then this is a 3D visualization. So from the center to where the disc, right, you project the end back to the same axis of rotation, right? That will be our small r. And this small r will keep changing as we go along because it gets smaller and smaller. Okay, so this r equals to square root r square minus x square. That's Pythagoras theorem. Basically, why we do all this, right? Again, we want to find out some relationship for dm and something that is doable. Replace the t. Okay, so down here, same thing, just that we will make use of our result for the previous derivation, right? We already know the moment inertia from the so we will continue from there, but we will still have this m that we need to replace. Okay, so if we go and replace and then go and integrate, you will get an expression like this. Okay? It's not too complex. 2/5 mr squared. So this is the moment inertia for solid sphere. So if you have a solid sphere, that means the whole thing has material. That will be the moment inertia. Okay, you rotate about the center point. Okay, so that's how we calculate moment of inertia. How we calculate moment inertia. There's this thing called the parallel axis theorem. It is to help us know the moment of inertia if the axis, right, does not pass through the center of mass. Okay, so you'll see examples of it, then it will be clear. Moment inertia of any axis parallel at a distance d away from the axis that passes through the center of mass, given by this. Okay, so the new moment inertia equals to the ICM. ICM means moment inertia when the axis pass through the center. Okay, and this is the original one, plus md squared. We want to know what is the new moment inertia if we rotate about another axis that is parallel to this original line, but at a distance d away. This is what you will do. Take the original one plus md. Okay, so let's see how to apply this parallel axis system. What is the moment of inertia? Cylinder about an axis on H. So this is a cylinder, right? Just now we already know the moment inertia if we were to rotate about the center. Correct? We have found out that ICM for a cylinder half mr squared. Okay, this is the moment inertia for the shape. But now we are not rotating about the center. We're rotating about the side, one end of it, like this. So this whole cylinder will rotate around this set. How do we find the new moment inertia? We will take the original one plus md squared. So original one is half mr squared. Then you will plus another md squared. What is the d here? It's your radius, right? Because the distance from the original one to the new one is r. Okay. That's why plus mr squared. So if you go and plus this together, right? This 3 over 2 mr squared, this describes this cylinder but rotating about this new axis. And okay, so this is how we make use of the parallel axis. Some moment inertia we already know, right? But now we want to rotate it about another axis. Just do one more step. Don't need to go and recalculate everything. Another example, what is I of a sphere of radius A for the axis A over 2 from the so a sphere, a solid sphere, right? Just now we know the moment inertia about its center, correct? The general one. That is 2 over 5 mr squared. In this case, the radius there is A again. And now we want to shift the axis A over 2 away. We want to rotate about this. How to find? We use the parallel axis. Okay, the original one plus m. So original one is 2/5 ma squared plus m a over 2. This is our distance. away, right? From the old to the new axis. Square. Okay, if you work it out, it looks something like this. Okay, so now that's your understanding a bit now. Okay, 7 coins are arranged in a hexagonal planar pattern so as to touch each neighbor as shown in the figure. Each coin is a uniform disk of mass m, radius r. What is the moment inertia of the system of 7 coins about axis that passes through the center of the central coin, normal to the plane of the coin? So you have these 7 coins, right? 1, 2, 3, 4, 5, 6 plus the one in the middle, that's 7. If you rotate about this axis that pierce through your screen now or your paper, right? So this whole object will be rotating, right? What is the moment of inertia for this entire object? Okay, take another maybe 2 minutes to try it out. We think about the concept. Okay, so let's see how to solve this. Then. So we have 6 coins around and one in the middle, right? First, we need to go and see. We take a look at one of the coins at the side first, okay? Let's look at this one. For example, this one. This one. You see, this is a coin rotating, but it's at a distance away from the original axis, right? The new axis is at a distance away, right? This is our r. This is our r. R is their radius. So for a moment of inertia for one of the coins at the side, is the original one. What's the original one for the for this is our half mr square, right? There'll be more inertia for a standard um, coin. But now we are at a distance away, so we need to do the parallel axis. Okay, so we need to plus our md square. What is the distance away? Distance is 2r away, right? 2r away. So this original one plus md square, this will account for one coin at the side. And this will give us 4.5. So that's for one coin, but you have 6 coins, right? So the final answer, you need to do 6 multiply 4.5 miles square. That's accounting for all 6 at the sides. Then don't forget there's one more at the middle. They're passing through the center of mass, so that is just a half miles square. Okay, so the answer for this, you will get 27.5 miles square. So this will be the moment of inertia. Okay, for this structure, they think about this point. Okay, any questions? So basically, this is our applying our parallel axis. Okay, okay, then we continue on the slides. So after this, right, it's just a summary of different shapes, the moment inertia for. Okay, so this one we have gone through already. Hoop, a hollow cylinder is a general formula. Solid disc, rectangular plate, we never show the derivation. Okay, but this is quite this lah. So the ICM for rectangular plate is based on long thin rod about center. Remember the rod rotating about center is 1/12. If you do at the side, right, it's much higher at 1/3 ml square. Okay, and solid sphere we have gone through with mr square. This one, thin spherical shell, that means it's also a sphere, right? But inside is hollow one. Okay, if inside is hollow, then it will be 2/3 mr square. Okay, and then there is this thing called the radius of gyration. It's just a concept lah, just to sometimes we see this radius of gyration when we deal with motion. So what is the definition of this? Actually, you just need to know the definition. And so if it's they ask you to find, right, or if you are given this, you know that it has got to do with the of use. So this radius of gyration is the distance from the center of mass of body at which the whole mass will be concentrated without changing the moment of rotation to the center of mass. Basically, right, what it's trying to say is imagine you have an object here. This is an extended object. Then you're rotating about this point. So there is a moment inertia to this, right? Okay. Then the radius of gyration of this is you imagine the same axis, but now you have a point with the same mass. You have a point with the same mass. Okay. Then at what distance away from the axis must this point mass rotate, right? Such that it will give the same amount of moment. Okay, basically this distance away, right? This is our radius of gyration. Moment inertia is mr square, right? That's why point inertia equals mk square, because this k, right, is actually distance from the axis to that imaginary point. If it were to point that is okay, so this is just by definition is the radius of gyration. Okay, then yeah, let's go through 2 questions again. One is easy, so we need to go through. Let's look at question 2. Energy is to be stored in a 70 kg flywheel shape of a uniform solid disc with radius 1.2. Prevent structural failure of the flywheel. Maximum allowed radial acceleration of the point on its rim is 3,500. What is the max kinetic energy that can be stored in the flywheel? So we need to know that the kinetic energy for rotational part is half I omega. Okay, half I omega square. And this thing is rotating, right? So the radial acceleration will be equals to r omega. So from this, right, from this, you will be able to know the angular velocity. So because they tell you the max allowed radial acceleration is this value, and the max allowed value, we should look at the most outer point, right? At the most outer point, you will experience the highest acceleration. Okay, so the R will be using it directly. So using this formula, radial acceleration r omega squared, we will be able to calculate our angular velocity, okay, which is angular velocity. And now for this half I omega squared, we have already gotten the omega, right? What's left is this I, moment inertia. So how to find the moment inertia? They tell is in the shape of uniform solid disk. So moment inertia on this is half mr squared. You'll go and calculate, and then go and put into this formula. You'll be able to find the kinetic. Okay, let's go through one more question. Okay, question 4. A thin rectangular sheet of metal has mass m and sides of length a and b. Illustrated here. Use the parallel axis theorem to calculate the moment inertia of the sheet for an axis perpendicular to the plane of the sheet and that passes through one corner of the sheet. So rectangle, our ICM for the rectangle is given by, okay, 1 over 12 m a square plus b. Then now we want to apply the parallel axis because initially the original is stating about the cm, right? Now we want to rotate about one corner. So we need to do the parallel axis theorem and we need to find out this. So what is this distance? Just use the Pythagoras theorem. One side is b over 2, one side is a over 2. So you'll be able to find what is the distance. So once you have this d, you just use a parallel axis theorem directly. Okay, ICM is this one, the original one, plus md squared. The d, right, will start inside here. Okay, whatever expression you get in the end is for this new setup that you are going to rotate about one end. Okay, any questions? If not, then take a short break. Don't need to go. Later we just go through one more short topic and then call it a day. Yes. Okay, is that better? So let's take a short break. Maybe we can start again at 8 p.m. Okay, 8 p.m. And to stay inside this session, I'm going to mark attendance now. So just stay inside this session. I'll mark whoever is inside. Okay. So see you all later at 8 p.m. again. Okay, thanks.
Life is You and me repeat, this bittersweet heat is suffocating. I'm waiting and always hesitating. Kryptonite desires set my heart afire. Heart on fire. Set my heart afire. Connect the dots straight to the start of intoxicating want. Lingering touch, these soft words whispered in the dark. Set my heart on fire.
Okay, hello. Yeah, welcome back. Let's move on to the last topic for today. As you can see, we should be ending early for us to move forward. So after this topic, right, maybe I'll briefly go through um, the assignment. Okay, very briefly go through the assignment. Okay, so let's go through this topic first. Now we're moving to rotational dynamics. So same thing like our linear kinematics, right? After we study kinematics, what we do, we go and learn about forces, right? So that's exactly what we are going to do now. After knowing the rotational kinematics, we are going to look at um, how are the forces involved, right? When we rotate something. Okay, so if we rotate something, there's this thing called the torque. Okay, consider a force F acting on a rigid body at point P in the direction as shown. So imagine this object, we are rotating about point O. So this is the rotation. Okay, imagine we are rotating this. You apply a force pulling it upwards. Okay, but because it's fixed at point O, it is a rotation. Okay, it is a rotation. So it must be going this way. Right, must be going this way. the torque of force F about point O is given by this force times your L. Okay, essentially, it is the force times the perpendicular distance away from the pivot. Okay, so F is here, right? This is the perpendicular distance. Okay, so the perpendicular distance is our R sine phi. Okay, down here, this is R sine phi. So you'll be taking this F times the perpendicular distance. Okay, so that's our torque. Basically, force times the shortest distance, which is the perpendicular distance. Torque may also be denoted by Sm. When we write as M, right, actually it's the same thing. It's our moment, but that is referring to our torque as well. If you are taking your mechanics now or have taken mechanics, this will be very basic for you, okay? It's almost like a revision. Okay, so same thing, that's torque. L is the moment arm or the lever arm of the force, which is the shortest distance from O to the line of action. Okay, this is the lever arm, shortest distance. Only the component perpendicular to R of the force causes rotation. This is another way to see it. Just now we see it as F times perpendicular distance, right? But you can also see it as this F, right? If you go and resolve into F sine phi and F cosine phi, only this F sine phi component, right, causes the rotation. Only this will be used to calculate the torque. So if you use this, right, what happens? If you take F sine phi times the perpendicular distance, which is R, you are going to get back the same thing. All right, you're going to get back the same thing. So it's the same. Two different ways of seeing the same thing. Component along R, F cosine phi, which is this one, it has no effect in rotation. It's like trying to stretch this thing, trying to pull this thing, bring into tension, but actually it does not cause rotation at all. For torque, right, we are talking about the one causing the rotation. So torque is a vector. If two or more forces are acting on a rigid object, it is assumed that the sign of torque is positive if the turning tendency of the force is counterclockwise and negative if turning clockwise. So this is just convention. Actually, at point O, right, this object. At point O, this is the rotation pivot. For point A, right, if you apply a force F, try to pull it somewhere to the top left. Okay, because this is counterclockwise, can you see that it's bringing a counterclockwise motion? This will be considered as positive torque. Okay, so this F1 multiplied by L1, this will be considered a positive torque. Whereas you look at point B, you have the F2 pulling away. But you see this F2 about point O, right, is producing a clockwise torque. So this one conventionally, we are going to write it as negative. And this F3 directly apply across the pivot. It's not going to bring any rotation. So there will be no torque. It will create no moment. Okay, so the summation of torque for these three forces, right, from these three forces, it will be summation of all the torque. Torque we write as tau. Okay, tau. It will be F1L1 minus F2L2 because this is positive, this is negative, and this is 0. Okay, so this is the summation of torque. Okay, so this is the convention that we use, and just stick to this convention. It will be the easiest. So what is the difference between torque and force? Forces can cause a change in linear motion. Forces can also cause a change in rotational motion, but the effectiveness of the forces in causing this change depends on both the force itself and the moment arms of the forces. That means it depends not only on the magnitude of the force, but also how far it is applied from the pivot. Okay, the shortest distance away. So it's actually this force that results in the torque. Torque is the force times the perpendicular distance. Here the dimension of torque, because it's force times distance, right? It's actually force times length. But when we write torque, the unit is Newton meter. Okay, we write it as Nm, not joules. It has the same dimensions as energy, if you remember. Energy is force times distance, right? Actually, they have the same exact dimension, but units is different. Okay, so we see Newton meter, we know we are referring to torque or moment. Okay, so now we consider a particle mass m rotating in a circle radius r. Down here, imagine we have this mass m, it's rotating like this, okay, with the radius r. We have a tangential force here, and because it's circle, right, we have a radial force. So the torque is causing the rotation. The torque will be your Ft times this distance, right? Ft is the force causing the rotation times the radius, which is the distance. Okay, so we will have your R times your Ft. Then this Ft tangential force, right, you can rewrite it as ma because F equals to ma, correct? And then we can further rewrite it. Tangential acceleration is your R alpha. Remember, A equals to R alpha, then in the previous set. So down here, you can pull the R inside. So the first part will look like mr squared times alpha. And remember what is our mr squared? Of course, you'll remember that because we just did it before the break. Okay, so mr squared is actually our moment of inertia. So in the end, right, you see torque equals to I alpha. Does it look very familiar to our linear part? Linear part, we have F equals to ma. So when we talk about rotations, the F is analogous to torque, right? M is analogous to I, A is analogous to alpha. Okay, so it's about the same one, looks very similar. Torque equals to I alpha. Okay, then for an extended object, this is a real rigid object with a lot of points. We go and sum up and do an integration, right? Which I'm not going to go through. Basically, is to tell you this formula stays the same. Okay, so this formula is proven to work for extended objects as well. Torque equals to I alpha. Okay, and we'll be using this now. Of course, we'll be using this quite a bit for rotations. It's like we use F equals to ma quite a bit, right? For linear motion. Same thing for rotations, torque equals to I alpha. One example, a uniform rod of mass m and length L attached to a frictionless pivot. When released from rest from a horizontal position, what is the angular acceleration? And what are the linear accelerations of points B and C? So it's pivot here. Now the center of mass is here, right? That's why the mg is drawn in the middle. And then if you release, this thing is going to swing downwards. Right? It's going to swing downwards. So they ask you what is the angular acceleration and what are the linear accelerations of point B and C. About pivot, we can make use of this formula. Okay, torque equals to I alpha to help us find. So first we're going to find out what is the torque of this setup. Okay, the torque that is bringing this rod down. It will be the force, which is this mg, applied in the middle, right? So it will be the force times the distance. Okay, force is mg, particular distance, it will be your L over 2. So our torque will be mg L over 2. Okay, then to use the formula, we also need to know for this setup with the pivot at the end, right? What is the moment of inertia? Essentially, what is the I? Okay, and we know that that is our 1/3 ml squared. Okay, this one, of course, you'll remember also, right? Because we just did it. So that is our I. Now you have your torque, you have your I. Can you find your alpha? You can, right? It's from the formula. Torque, so tau equals to I alpha. In this case, we want to find alpha. So we make alpha the subject. Let's take this torque divided by I. You're going to get your angular acceleration. Okay, so that's one part of the question already. And they ask you to find the linear acceleration of this point and this point. When you have your angular acceleration, to find the linear, right, you just have to multiply by the radius. All right? They will have the same angular acceleration every point, but different linear acceleration. So it depends on the distance from the pivot. So of course, B, you will take the distance you will take is the entire thing because B is here. That's your L. That's why L times this one. And for your C, right, you will take L over 2, that's the distance, times this angular acceleration. Okay? Yeah, then we move on. Video, actually not really video lah. Okay, basically is let you think about it. Tie another mass to the rod at the end as shown. It's the same question as just now, by the rod. But now you go and tie one new mass at the end. Which rod will take a shorter time to swing to the vertical position? You release this rod from rest, right? It will go down, become vertical. This one also will go down and become vertical. But you go and add one mass at the end. Which one will swing to the vertical position faster? Okay, so to find out, we can compare the angular acceleration. Of course, the one with a higher angular acceleration going to reach there first, right? So just now we have already gotten angular acceleration for this, so we're not going to go through again. Right? It's the follow the same method, so you get the same angular acceleration. But if you go and tie a mass at the end, right, the torque and the I will change. Okay, so now the torque is the original one, plus you go and they have another mass at the end. So you need to do another F times your perpendicular length. So the force is your small mg times the entire L. So now the torque of this, right, is there's another term coming out, is greater. And then the moment of inertia is the original one. And this one is almost like a point, right, at the end. So that is, to find the moment of inertia, you just need to plus your ml squared. Basically mr squared, because moment of inertia is a mr squared, right? This is almost like a point. So you just take m, r is the whole thing. So if you go and use the same method, right, you will realize angular acceleration equals to this. You see the left hand, the one on the outside of the bracket, right? It's the same as this, but the one inside the bracket, the numerator is smaller than the denominator, correct? Which means this alpha is gonna be a smaller value as compared to this. What does it mean? This angular acceleration now with the attached mass is lower than the original one. So if you go and put a mass at the end, right, the acceleration will be lower. So it will take more time to reach vertical position, which is not very intuitive to most people, right? You will expect, you tie one more mass, it should swing down faster, right? But no, that's not the case. Okay, because why? If you go and tie one more mass at the end, right, you are increasing the moment of inertia of this system by a lot. Remember, we say if we push mass to the furthest, to far away from the trigger, right, we are going to increase the resistance to rotation. Okay, so in this case, you increase the resistance so much that it cannot accelerate as fast already. Although it's supposed to have more force trying to pull it up. Okay? Okay, just another example with illustration only. For example, we have this structure here with a string. They want us, so if nearer to the pivot, it will be faster. Yeah, correct. Actually, you went work out the solutions, practice on your own, and then you see, you compare the alpha. And that will give you the answer. Okay? Yeah, good question. Okay, we come back to this example, unwinding cable. Want to find A, alpha, and T in terms of I, R, and M, given this structure. So we have this sort of wheel here. Okay, then you have a string inside tied to this mass here. Okay, so imagine if you release, of course, this mass will be released down, right? And then this string will follow suit. Okay, then there will be a rotation to this. Okay, so the systems they are connected together. And then A pointing down, this is the linear acceleration. So if we look at this structure here, right, the one at the top of this is given by T times R. Okay, there's a tension here. This is the pivot, right in the middle. T times R. Okay, that is the top. And then we also know torque equals to I alpha. We also know linear acceleration is related to angular acceleration in this manner. A equals to R alpha. So from here, right, we can write linear acceleration in terms of T and R and I. We do this so that later we can substitute somewhere to replace something. Okay, so this is what we already know. So down here, if we draw a free body diagram of the weight, they are connected systems, right? But now we isolate the weight. And then we draw a free body diagram. We have mg pointing down, t pointing up, that's why you minus t. And then this whole thing is accelerating with accelerating with a, right? So equals to ma. So the equation will look like this. Down here, we want to replace this a with the one we have just derived. Okay, so you're going to replace that a with tr squared over I, and then there's 2t here, right? You go and make that the subject and go and solve for the expression. You'll be able to find an expression for the tension in terms of I, R, and M. Okay, once you have the tension ready, if you want to continue finding your linear acceleration or your angular acceleration, right, it will be easy already because they are all related here, right? Basically, if you have t, to find a, you just have to multiply by r squared over I down here. If you want to find angular acceleration, you will just use this one. Okay, because you already have a plus divided by r to be able to find angular acceleration. So this is just to roughly show you. So if systems are connected, you can make use of different info, combine them together, and then solve for what you need to find. Okay, so that's our top. And same thing for rotation, right? Just like our linear counterpart, there will also be work, which is energy. Okay, there will also be power and energy. Work is like work done, but it is energy, right? As we have learned. So consider a point rotating through distance ds. Let's say we have a point here, right? We're rotating about pivot O. We have rotated a distance of ds. The force is applied upwards. What is the work done? It is our force times distance, right? Or rather F dot S. So it's our F dot S. And because it's dot product, right? It will make sure only the one in the same direction will count. Okay, only the one in the same direction will count, which is why you will get F sine phi, because you resolve this F to the one in the same direction as where the distance is going. Okay, F sine theta is this one. Theta is here, right? So F sine theta is in this direction, okay? Same as this one. Okay, that's the one you want to know. And ds will change to r theta because s equals to r theta, right? That's why we change into that form. So in the end, we are going to get work done equals to tau times theta. Okay, so you see, you compare to what we have learned, right? Last time we learned that work done equals to force times distance, right? Now, work done for rotation equals to tau times change in theta, which is the angular displacement traveled. So you see the similarity is the same again, right? So basically, you just change it to your angular quantities. Okay, you're going to get the same thing. Okay, so that's work done. And then for power, it is our work done divided by change in time. This work done, right, you can split it out again from here. Tau d theta over dt. In the same manner, d theta over dt is going to give you your omega. So in the end, power is also equals to your tau omega. Remember in our linear part, power equals to what? Power equals to force times velocity, right? You can see it's very similar. And last time down here, work done equals to force times distance. Also very similar. Okay, so if you realize, if you know the linear quantities well, right, and the linear calculations well, right, come to rotation, actually it's okay one. Okay, it's okay one because it's very similar. Basically, it's derived from linear, whatever we learn in the linear part. Okay, that's why we end up with about the same thing. Okay, then we come to work and energy. The net work done by external forces in rotating a rigid object while fixed axis equals the change in object's rotational energy. Same thing, this is the conservation of energy statement. The work done, that means the work that you supply to something, right, must go into changing the rotational energy, rotational kinetic energy of the object. Okay, down here we start with tau equals to I alpha, because now we're in rotation, right? Basically, we keep changing. Okay, in the end, I don't want to confuse you with the first three steps, because we are not exactly doing mathematics. Okay, we want to study concepts. So in the end, right, we're going to get this statement here. This is actually very similar to what we have learned in the linear part. So work done, that means the energy you do to something, like you give something, the work done must be equals to the final rotational kinetic energy minus the initial rotational kinetic energy. You see, this is actually just conservation of energy. Okay, final energy minus initial energy. Last time is half mv square, right? Now we are talking about rotations. That's why it's half I omega squared. Then we look at one example. A uniform rod of length L and mass m is free to rotate on a frictionless pin passing through one end. The rod is released from rest in the horizontal position. What is the angular speed when it reaches the lowest position? That means from here, right? You swing until this vertical position. Of course, it will still be swinging, right? But they ask you at this particular position, what is the angular speed? Okay, part B, determine the linear speed of the center of mass and the linear speed of the lowest point of the rock when it's in the position. So down here, they ask you to determine the speed of the linear speed of this point and the linear speed of this point. Part A, calculate the linear velocity first. Now here we can use the conservation of energy. Basically, the final energy must be equals to the initial energy. Right? So final kinetic energy, what we have, final is at a vertical position. This thing is moving, it's rotating, right? That's why we have half I omega squared. Then at the final point, the potential energy will treat it as zero. Can you see that it's moving from a higher point? From a higher point, to a lower point, down here from a higher point to a lower point. So we will be taking this as the reference. Okay, remember for potential energy, we can just take any as the reference. Usually we just take the lowest point as a reference. We set that to 0. That's why final potential energy is set to 0. Then the other side, initial kinetic energy is not moving, right? So it's 0. How about the initial potential energy? Initial potential energy is from this height move until this height. Okay, so if we set this at 0, this one will be our mgh. Then the h is your L over 2, right? That's why it's given here. So from here, just go and solve for your omega. That will be our angular speed. That will be our angular speed. Then for part B, they ask you to find the linear velocities, one at the middle part, one at the end. This one is the easy part. When you have angular velocity, very easy to find linear velocity, right? Because we know V equals to R omega. Right? V equals to R omega. So we just need to multiply by the respective R. For Cm, the R is L over 2. For the one at the end, call it the V tip, is entire length is the R. That's why it's L omega. Okay, another example. Consider two cylinders having masses M1 and M2, where M1 is not equal to M2. So we have this pulley system here. And then M1 and M2, they are different mass. So if they are different mass, what will happen? This thing will move, right? This thing will move somewhere. Connected by a string passing over a pulley. The pulley has a radius R, this one, radius R, and moment of inertia I about its axis of rotation. So this pulley will start to turn also, right? In either direction. The moment it turns, there will be some energy to it. Correct? Because if it has some if there's some turning, there will be some rotational kinetic energy to it. And then that half I omega square will be more. The string does not slip on the pulley and the system is released from rest. Find the linear speeds of the cylinders after cylinder 2 descends through a distance h and the angular speed of the pulley at this time. So they tell you this 2, right, will move down to here. Of course, if this move down to here, this M1 will move up to here. Then they ask you to find the linear speeds. So how to do that? We can use the conservation of energy. Okay? So same thing, final energy equals to initial energy. So final energy, what we have for the kinetic component, we have this mass one moving, right? It's still moving, correct? So we have a half mv square. For mass 2 is also moving, so we need to account for that. Half mv square for the mass 2. And then what else is moving? This thing is moving, remember? This thing is going down, this thing is going up, and then this thing is turning. This pulley is rotating at that moment when we are analyzing. So we need to account for that. That will be given by our half I omega square. Here is rotational energy. Okay, that's our kinetic final energy. So for the final potential energy, right? What do we have? We have M1 already move up a distance of h. That's why we have mgh plus because you gain potential energy. Then for M2, we move down a distance h. Okay, we move down a distance h. That's why it will be a negative here. We lose potential energy. Okay, then the initial, we just assume that there's nothing. Nothing. It's not moving, and then the initial one is for reference. So it's 0. So from here, you will solve for what you want to solve. And this omega, you also know that it is related to the linear velocity by this formula. But you can change so that you will have less unknown for you to solve. So if you go and sub v equals to r omega inside here, okay, so you will look like this. This omega will place already. Down here, right, in this particular equation that you see here, there's only VF, which is the unknown. So we're going to make that the subject and then go and solve for it. On the right is if you have your VF ready, to solve, to find out your omega, very easy, just refer back to this. If you have this, you can get this. Okay, that's what it is. Okay, so let's go through two of the supplementary questions before we talk a bit about assignment. Here we are super ahead of time. Okay. Question 1. Calculate the net torque about point O for the two forces applied as in the figure shown. The rod and the both forces are in the plane of the pitch. So we have two forces, the pivot is here. What is the net torque? Consider easy question. So we just need to do a summation of torque. Torque we know is force times perpendicular distance, right? So we just need to know for F1, what is the torque? Tau1, which is the torque due to F1, it will be minus F1 L1 because remember, when it's causing a clockwise movement, it will be negative. So you take minus 8 times 5, the whole thing. Then for torque 2, it's positive because it's causing an anti-clockwise movement. Okay, so if you do that, but make sure you have this sine 30 over here because you want to take force times the perpendicular distance. Perpendicular distance is this one. Okay, this is our perpendicular distance, which is why we have a sine 30 to account for that. Okay, then basically net torque means you sum up the torque together. Tau 1 plus tau 2, it will give you minus 28. So if you get a negative value, right, you'll know that the torque is going clockwise. Okay, so in other words, this F1 will win. So you'll be pushing it clockwise. Okay. Any questions? There we go through question 2 also. A machinist is using a wrench to loosen a nut like this. Because a wrench is a nut trying to loosen it. The wrench is 25 cm long and he exerts a 70 Newton force at the end of the handle at 37 degrees with the handle. What torque does the machinist exert about the center of the nut? What is the maximum torque he could exert with this force? And how should it be oriented? So what is the torque exerted for this one shown in the picture? You'll be taking force times the perpendicular distance. Okay, so force is already what we have. Perpendicular distance is this one. Okay, this is our perpendicular distance. Imagine there's a line here. So this is a perpendicular distance. That's why you need to have a sine 37 component here to account for that. Okay, and obviously the torque is counterclockwise. Then for part B, what is the maximum torque you could exert with this force, and how should the force be oriented? The max torque should be when this angle is 90 degrees. Alright. If he can apply 17 Newton, he should not have applied in this manner. He should apply where this angle is 90 degrees. That will get the maximum torque. In other words, he is wasting energy. So he should have been applying like this. Alright, he should have been applying like this. If this is 90 degrees, right, that will give you the max torque. Okay, because you apply at the furthest end plus you make it 90 degrees. So that's the way to turn the nut. Okay, so if you go and build your own IKEA furniture, that right, remember to always hold at the end, and your force right apply perpendicular. Waste your energy unless you want to gym lah, you want to waste energy. Okay lah, can. But if you want to have easy life, always hold at the end and apply perpendicular direction. Some technicians outside, I'm not sure whether you notice that they never hold at the end. Some like to hold near where the nut is. Their hand they hold here. They're wasting a lot of energy lah, actually. Of course, they can overcome the resistance lah, but actually they are using a lot more energy than is required. Then the other questions, yeah, you all can go and look through. And if you all got any questions, can come and ask me. Okay, but should be okay lah. Should be okay. If you read through and don't know, right, think a bit first lah. Think a bit first, like what kind of equation is there? Where is it from? What kind of concept is there? If you figure it out on your own, right, actually that's a better way to learn. You confirm remember it for a longer time. Okay. Any questions for this topic or rather these three topics? Before I just briefly go through the assignment again. Okay, I think everything good, and I will post this and open the assignment. Okay. Okay, so this assignment is your assignment one. Okay, so you should follow the instructions lah. You should follow the instructions. But that time I say one thing to note, right, is I want to make your life easier. So you see this part here, right? Solve A and B using analytical methods. This is the only one out of the two that I want you all to do. I want you all to use analytical methods only. Okay, part B is use working model simulation. This one requires some software, which I don't require you all to use. Okay, so you all only need to show workings and then do it normally like how you all would do a tutorial or exam. Okay, that is what we mean by analytical methods. So this part, we only need to do analytical methods. Okay, and then the ones below, right? Compare the results found by these two methods and estimate the errors in percentage. This one actually is referring to analytical and simulation. So there will not be any errors because we are not using simulation. We are only having analytical methods. But if you look at the question, right? Look at the question. I believe all of you should have read the question, all right? So in each part, right, they ask you to use different methods to do it. They ask you to use different methods to do it. So you will, in the end, you will still have things to compare. I want you all to compare that and then write a few lines about it. There isn't one right answer. There is no one right answer. It's not like physics and maths, right? The answer 62 means 62, but this one you write in sentences. If it makes sense, right, you get the marks. Okay, so for example, remember there's this pulley question that we solve using energy. and using force also. Like you can see the energy one is so much easier to solve than using the force method. Correct? But then you still have to think of the relative velocity, how much you pull the rope relative to the person. In the end, what you get the same answer. So you can compare the methods. Which one easier? Why is easier? Why in that case you will be using? Why is this easier in that case? So that's qualitative, like writing in words. Okay, so in the end, you still have to discuss. But already reduce your workload by a lot already. You don't need to do the simulation. That one, you all still have to go and find the software, go and do it. But that one, don't need to do. Okay, so I'll briefly go through the question. Okay, part A is this illustration here. A pulley rope mechanism is shown in this figure. In order to lift the block A to a certain elevation, that means you lift it up, right? A force F is required to apply to the end of cable at point B. That means this point B, if you pull it down, point A, you can imagine it should go up, right? That's what it's trying to say. The mass of the block A is 200 kg. The masses of pulley B, C, E, they are, and the rope are negligible compared to the mass of block A. So they are trying to tell you the ropes and the pulley, they are massless. Okay? The friction of the pulley rope also can be neglected. So it becomes a quite straightforward kind of thing. Quite straightforward kind of thing. But there are a few pulleys involved, so be careful, okay? Part A, in two ways, determine the constant force F that is required to apply to the rope at point B in order to lift the block A to reach speed of 10 meters per second and displacement of 5 meters upward from rest. So imagine they are in this setup already, right? To raise this block A by 5 meter upwards, and then at the point where it reach 5 meter, it must achieve this 10 meters per second. What must you apply at B to achieve that? Okay, that's what part A is trying to ask you to solve. So you can use force and acceleration to solve it. They already hint you is Newton's second law of motion. That is your F equals to ma, right? And then also you will use work and energy principle. This is basically the conservation of energy, okay, to solve this problem also. And logically speaking, you should get the same answer, right? Analytical methods should be perfectly same answer. So if you get two different answers, it is very obvious at least one is wrong. It could be both wrong, but obviously at least one is wrong. You should get the same answer. If you are trying to solve for the same thing, you should get the same answer. Okay, so that's part A. Part B, in two ways, determine the velocity and distance of block A and point B in time t equals to 4 seconds if the applied force at point B is 90 kg. Consider the system is released from rest. So imagine this point B, let's say you attach a 90 kg from it. At that instant, right, you release from rest. 4 seconds later, right, what is the velocity and distance of this A and this B? Okay, same thing, use two different methods to solve it. Force, acceleration, kinematics, that's one method. Also use your impulse and momentum methods. Remember your conservation of momentum. Okay, so we'll be using this to solve it. Again, you're finding the same thing, so you should expect the same answer, right? Okay. Michael asks, can the assignment be handwritten for the problem solving part? I would say preferably not. It's not no, because you handwritten, right? Usually students will think it's legible, can read, right? But actually very hard to read. And in the end, don't know whether it's correct or not. Okay, so there will always be that discrepancy there. Some cases where student think can read, but we cannot read. We cannot read. Very hard to tell. In that case, maybe you lose some marks, then not worth it. Okay, so to prevent this kind of situation, if you type it out, right, confirm no problem with it. Because you type out whatever you type is confirm you can see one. Okay, so recommended to type out. Recommended to type out and then also try to underline your final answers. Okay, so it looks obvious. In case miss it somewhere. Maybe you write in another column. Okay, then I think there's a typo in the formula B2. B2, which is the typo? Yeah, I think you're right. Wait, let me see. Principle. Yeah, should be a plus. You're correct. Good. Do I get extra points? I'm sure you will do it well, so you will get points there already. Okay? Because you spot this kind of thing. Okay, basically, why is it like that, right? Is initial momentum you plus whatever impulse added to it, right, will be equals to the final momentum. Okay? It's a bit like conservation of energy, right? Okay, okay, good. Okay, one good. But anyway, use your understanding of impulse and momentum. Don't need to follow this kind of confusing formula. Also should be able to solve now. Okay, this is whatever we have gone through. Okay, then the next question. The ping pong ball has a mass of 2 kg. If the ball is struck with the velocity shown, determine how high pitch it rises above the end of the smooth table after the rebound. So it starts from here, going down with a 30 degrees, right? And then the distance travel is 2.25. After the rebound, the distance travel only 0.75. Then you have to find the height h. So you can see this is from what does it look like? Looks like projectile motion, right? Looks like projectile motion. And then down here, what kind of concepts? Actually, they give you a hint really. They say take E equals to 0.8. Remember what is E? That's our coefficient of restitution. Right? Forget, never mind. Go ahead and pick through all the notes. Confirm will find. Okay, it gives you a hint of which topic is it from. Okay, but you have something, you hit something and rebound. I think most of you should know which topic should it be. Okay? Restitution, coefficient of restitution. We have gone through it before. It's in the notes also. Confirm can find. Okay? Okay, yeah. So remember to submit before the deadline. This is following RMIT, so there is a 3 hours difference. If I remember correctly, what we are seeing is 8 p.m., right? Correct? I think it's 8 p.m. That means by 5 p.m. you all need to submit really. Okay, but to avoid this kind of thing going something wrong, right? Don't submit so soon lah. Maybe one day before or a few days before, try to finish and submit already. Okay. Any other questions? Very good question. Why ping pong ball so heavy? Because not I said one. That makes no sense lah. That was also what I thought. But anyway, yeah, just take it as a practice. Okay, any other questions? Yeah, so today end quite early. Anyway, yeah, if you have any questions, right, like this, like when we end early, right, you can kind of ask me questions. Yeah, because actually we have a lot of time, but of course, if no one asks question, then we will close the session, that kind of thing. Of course, you feel free to email, but you can use this time to ask me questions as well. For today, you can see it's quite short. For the next two, I've already uploaded already lah, so you all can browse through the notes and get an idea of how long the lesson will last. Shouldn't be too long also. I don't know the exact duration now, of course, but shouldn't be too long also. Okay. And next week onwards, we will be going back to classroom. Okay, so we'll be going back to classroom for next Friday. And the last lesson will also be going back to classroom in a hybrid mode. There is any format for the cover sheet? No particular format. Just make sure I know it's you. Okay, just make sure I know it's you. So your full name, your ID number, write the module, write the assignment number. Any recommended reference book for self-study? Uh, Actually, how should I put this? Every course, right, there will be some sort of recommended textbook. But personally, right, my answer to this is there should be no recommended reference book lah, because the concept, right, is the same as any engineering dynamic books that you are going to find. Okay, because engineering dynamics, for example, when we are studying general physics, right, this kind of general module, every textbook or every book that you see, right, will tell you and study about the same thing. Even the topics, right, also about the same. Okay, so whatever book you use, we are going to get the same concepts. It's only at a very high level kind of special topics. Okay, a very high level special topics. Then the textbooks will make a very huge difference because different authors, right, will write about different things. But for a module like engineering dynamics or even mechanics or even like fluid mechanics one, like that, all these kind of general module, right, whichever book you refer for the concept and for their tutorial solution, right, is okay one. Okay, so there is no fixed book. Yeah, no problem. Actually, my focus, right, is always to um, try to let you understand the concepts, okay, rather than focusing so much on the mathematics part, or rather after this step is what step, after that step is which step. Okay, that is a very not so good way of learning things. Learning concepts is the best. Tips and tricks to study for exam. I can only say the exams, right? Your tutorial components, right, will be quite representative lah, quite representative of what you're going to get for exam. definitely will not be same or similar lah. But it's that kind of question. Okay? Got a picture and ask you to solve for something. Quite similar. Okay, which a professor or lecturer from RMIT will be taking you on. Okay. Any other questions? If not, then actually, yeah, I can leave already. You're gonna have a good rest. And probably hope to see you all face to face next week. Lah. Okay? But if you want to do online, can. Okay, yeah, so we can leave already. Yeah, thanks for attending. For attendance, yeah, let me see.